to record, just in case anybody wants to watch it who misses it. Halima got this all right, totally perfect, really brilliant. In this one here, I'm going to start here, CH, C6H5. This is polystyrene, CHH. This one is the same as this one. Stop here. Get rid of the rest of it. Put the double bond in. That's it. It doesn't matter if you had it the other way round. It doesn't matter if you had CHH double bond CH C6H5. It doesn't matter. It's the same molecule. It's just backwards. This one here is a little bit more difficult. We call this Teflon. This is non-stick material, or it's also the material in some coats, which makes it waterproof, but it still breathes. They invented this, NASA invented this for the front of space rockets, because it is non-stick. So the atmosphere moved past it really easily. So I start here. I remember I have to have 2 carbons, okay? So I just go here, CFF. Oh, they all look the same, but I need 2 of them, so I stop there. So there, what I do is this. That's it, okay? So I hope you all got that right. It's a good question to be able to get right. Not very difficult, but very important. Almost always worth 2 marks. Okay. The next question they ask about polymers is a calculation question. And the calculation question is here. I'll show you one. Here we are. So here's one. Okay. A sample of this polymer has a molecular mass of 5194. Determine the number of monomers in the polymer. Okay, so it's 5194. Now, this monomer, I'll just draw it on my board. I'll come to you in just a minute. Right, I'll come back to you. Okay. So it goes like this. You work out the monomer, firstly. You find out what the monomer is, the small one with the double bond. And then what you do is you go, okay, let's have a look at that monomer and see what it would be if it was just that monomer. So I go, okay, this here is 1, 2, 3 carbons. 3 carbons, 1, 2, 3 hydrogens, and 1 nitrogen. And I'm going to find the mass of this monomer on its own. So 3 carbons, that's 3, each carbon is 12, so that's 36. 3 hydrogens, only 1 each, 3, 1 nitrogen, 14, 6, 10, 13, 1, 3, 1, 53. Now, what do I do next? Well, next what I have to do is I have to look, it said that the polymer weighs 5194. 5194 is the length of the polymer, the whole piece. And so what I say is, well, how many 53s are there in there? So I go, okay, this weighs 53. So I need n times 53 equals 5194. This number is 98. So there are 98 of these to make the polymer. Now there's another example of that in the sheet of questions which I sent you, and I've sent the answers as well. So your supervisors can show you that if necessary, okay? That's another type of question. We'll go to another question and see if it's easy for you or difficult. So far, be able to recognize the polymer and chop it up to make the monomer, add the monomers to make the polymer, and this calculation, work out the monomer, work out its mass, what that weighs, in this case 53, and say, okay, how many 53s to make up 5194? Divide 5194 by 53. The answer is 98. 2 marks. So 4 marks, really easy for either looking at the polymer and making the monomer, or doing it the other way around, and 2 more for this. This question keeps on coming up on KCSE chemistry. So let's have a look at another question. Here's another question. A bit further on in the piece of, I hope you got the questions. If not, don't worry, because you'll get them later. That's the same thing. Here is the same type of question like the calculation, so you can have a go at that. Have a go, let me just see. I think the answer to this, if you want to write it down now, is 174, okay? If you have a go at this question, the answer is 174. So it's this question here, it's about polystyrene, and it asks you to draw the monomer, that's cut it up, and then it asks you to work out the number of them, okay? That's easy. Now, this is about a different kind of polymer, and I'm going to look at this one, and I'm going to look at these, detergents and soaps. So how many people find detergents and soaps and the other kind of polymer difficult? This kind of polymer is called addition polymer because they just add together. The other type is condensation. It's nylon, terylene, and things like that, and also proteins. How many people find the things like the structure of a protein or something difficult to work out? Is that stuff easy? This question's like this question. Like this question here. This one here, you have to work out what happened. Okay, the question is, what is the name of the linkage? What kind of polymerization is that is? Is this okay or not okay? Genesis? Hi, Genesis. Don't go yet. That's okay, is it? That's all right, good. Tumaini, is this okay? Okay, so I won't do that one. The next question is about soaps and detergents. Are you okay or not okay with soaps and detergents? Soaps and detergents. Genesis, soaps, detergents, yes or no? Oh, half and half. Some people definitely know. Tumaini, soaps, detergents. Are you familiar or not familiar? Do you want to do some, or are you okay? Tumaini?
Thumbs down.
I think it's mainly thumbs down. Thanks, Justin. How was your scrambled egg? Okay, so I'm going to look at a question here. Here, looking at this question here, this is about detergents and soaps, and I'm going to tell you about detergents and soaps, and it's fairly straightforward things, but it's important that you know how it goes and the sort of questions that you get. The first one says, here's 2 cleaning agents. Here's A, RCOO, Na+. It should have a minus here, but it doesn't. And this is B, R, this funny thing looking here. This is called a benzene ring. And then OSO3 minus Na+, okay? This is a different kind of chemical from this one. It says, which cleaning agent would be more suitable for washing in water containing magnesium sulfate, and explain? And it's 2 marks. And firstly, you have to be able to recognize what these 2 are. So I'm going to come back to my board and I will show you what they are. Firstly, the one like this is a soap. I'm just going to go through very quickly how soaps are made, because then you will know why they are different from the other one, which looked like this. Like this. And this is a soap, and this is a detergent. And I'm going to show you how they form, because it will make it a bit more sensible. Okay. Soaps are made by taking a fat or an oil and heat with sodium hydroxide in water. Now, fats and oils all have the same structure. The structure is an ester. Esters are made from alkanoic acid and alkanol, okay, joined together. And they look like this. They have this joining part. This, okay? It's always the same. This makes it an ester. In my classes, I tell people that esters are very pleasant smelling. They have a nice smell. So I say, where do we come across nice smells? And they say perfume, correct, and food, correct. Now, what do we do with food? We cook it. Okay, obvious. But this is a way to remember that this is an ester, because if you look at this, this could be written out COOC. It's incorrect spelling, of course, but it's like cook. So we use esters in cooking. So anytime you see COOC, that means it's an ester, okay? Every single time, COOC, ester. You see them in polyesters like terylene and viscose and so on, but you also see them in fats and oils. So here we go. This is what's happening. So a fat or an oil, they always consist of the same parts. They always have a long chain and another one and another one. And it doesn't matter what these are. These depend on what the fat or oil is. So from palm oil, you get a different kind of chain from the fat from a cow, let's say. Okay. So here there is a COOC, COOC, COOC. The COOC, like cook, makes it into an ester. But fats and oils have these three joined together, like that. These are called fatty acids. And this is called glycerol. When we heat this with sodium hydroxide, this breaks, and it breaks here. Okay, it breaks here. And what we get is these long and then COO, but it's not COOC anymore, it's COONA. And it's COO minus Na plus. So we get three of those. Like that. And this is the soap. And soaps are great. You know, soaps are really good for washing, but there are some places where they don't work properly. The other part we get is this bit. And this will be 3 carbons joined together. And it is 3 carbons, and each one of them has an OH. So it makes it an alkanol. And glycerol is very smooth. They often put the glycerol into the soap because it makes it smoother to wash with. But there is a problem with soap. And you may have come across this. When you use soap, sometimes it gets you clean, but there is scum afterwards. And the scum happens anytime the water contains calcium or magnesium ions. So if you have any compound containing calcium or magnesium in the water, don't use soap if you can use something else. Because calcium and magnesium precipitate, makes this scum, okay? So soap plus these makes scum. Scum is the just the stuff which is round the bucket or washing bowl or whatever, okay? So soaps, anytime it's with calcium or magnesium, don't use it. So the question is, from this question which I showed you, I'll just show you it again. I'll just share it. It says, I'll show you the other bit in just a minute. Here it says, here are A and B. There is COONA, that's soap. This one is different. This one is a detergent, but we'll come to that in just a minute. So soap, which cleaning agent would be more suitable for washing in water containing magnesium? Magnesium sulfate, magnesium chloride, magnesium anything, calcium, sulfate, calcium, chloride, anything, calcium or magnesium, we don't use soap. So explain, the point is that if you say, magnesium and calcium in water makes it hard water, and soap in hard water makes scum. So it doesn't make you as clean, okay? The other chemical is a detergent. And in a detergent, what we get is a different kind of chemical. It's made in a slightly different way. The point about it is that it is in many ways very similar to look at to start with, but instead of COONA, it's SO3ONA. Okay, and this is, it looks like this. Whoops, like this. And this makes it better at dissolving in water. So this is a detergent. If you were going to wash clothes and you had magnesium or calcium in the water, if you use a detergent, this is better than a soap because it will clean the clothes and it will not leave the scum which soap would. Okay, so that's the answer to that question. 2 marks, simple. So you say magnesium or calcium makes it hard water with soap, not with detergent, with soap would make a scum. Detergent, no scum, really clean, okay? Has anybody got any questions about that? Is anybody okay on that? Is that okay? Are we okay? Anybody out there? Let's hope it's okay. Here's another question from this type of this part of the specification. This one here is about down here. Oh, sorry, this question here is again about soap. Here it is. This is what I showed you. Look, COOC, that's cook, that is ester, okay? This is a fat or an oil, and it reacts with sodium hydroxide to make, this is what I showed as a wiggly line, a curly line. So it's COONA, that's the soap. This is the glycerol. We would call this prop and propanol, but it's 3 alcohols, so it's propan triol, and they're on carbon 1, 2, 3, so propan 1, 2, 3 triol, but that doesn't matter. So if you see one like this, what type of compound has this formula? COONA, that's a soap. Its use is for cleaning anything, me, you, etc. Vulcanization. I'm going to ask whether people want to do vulcanization. It's a fairly straightforward thing. And then I'm going to do a little practical and ask you the answers. So, vulcanization. Vulcanization of rubber. Is this okay or not? So, is vulcanization okay? Do you understand and know vulcanization, or do you not know vulcanization? Whoa, that was very quick. Genesis, are you to vulcanization, or are you yeah? That's 2 people going there, and 7 people have gone to sleep. Okay, Tumaini, are you okay with vulcanization, or is vulcanization, I don't know what you're talking about? I feel very sorry for you, Tumaini, because some of you obviously have no thumbs. It's hard, you know, because some of you, you're just like, oh, it's hard, hey? How you get a lift? Right, okay. So I'm going to do vulcanization. Here we go. Hi, Yestin.
Hi, Mark.
You all right?
Yeah, you can't see some of the thumbs in the light at the back, can you?
No, yes, you can't see them properly, but I've got the answer. Okay, vulcanization is what they do to rubber. Rubber, you know what rubber is. It comes from a tree, it's easy stuff. And it's long, thin chains. And the long, thin chains look like this. Okay? And they go on and on and on and on. They are very, very long. Very, very long. It comes naturally from a tree. And you will see now, whoops, from the way I'm drawing it, that it has single and double bonds. So rubber is like this. It's fairly stretchy when it comes out of the tree. It's a liquid when it comes out of the tree, and then they do things like they react it with formic acid, the acid that ants produce. You know, when they bite you and they sting, that is formic acid, methanoic acid. So they wash it and it becomes a solid, but it's no good. It's not very strong. It's a bit useless. So what they do, this was discovered by a man called Goodyear, who invented tires for automobiles, and he was in prison. And he was in prison for not paying a debt. And eventually he did this experiment in prison, and he found this way. So they react it with sulfur. And sulfur, you can spell sulfur P-H-U-R or S-U-L-F-U-R. Both are okay, okay? Both of them are okay. This was how they started to try and do it 10 years ago. We always did it like this. Both are correct. So they react the chains with sulfur, and what happens is this. The sulfur joins in between the chains. And what it does is it breaks a double bond here and a double bond here, and we get one sulfur and another sulfur and joined on. And it happens down the chain. Sulfur, whoops, sorry. Sulfur, sulfur, like this, okay? So it links between the chains. Now, if I got a lot of wire, yeah, and I made it like this, I could just move it and get through it. But if I put links between it, so if I get wire like this, it's easy to get through because I can just stretch it. But if I put links like this, I can't get through it anymore. It's the same with this. This is called disulfide links, or link or join or bond. A disulfide link joins the chains together. It makes it stronger and more flexible because it can do this, okay? Stronger and more flexible means it can make the tire for a car. This is very important. This is one of those things they have to ask you, okay? So vulcanization, heat with sulfur, 150 degrees, doesn't matter, with sulfur, and it forms these links between the chains. And you just have to say 2 things, 2 properties. 1, stronger, so the tire just doesn't break, and 2, more flexible, so the tire will bounce better, which is good. Okay, now I'm going to do a little experiment, and I'm going to ask you about this. So I'm going to do a little experiment, and I'm going to tell you what I do first, okay? So I have 3 chemicals, and the 3 chemicals are, we are going to call A, B, and C. Okay, very simple, A, B, C. I'm going to react them with potassium permanganate. Potassium permanganate is purple. It is an oxidizing agent. You may have come across it. You need to know about it. I'm going to react them with bromine water. Bromine water is very bad for us. I'm going to react it with bromine water. And I have a box of matches. So I'm going to set fire to them, okay? And we're going to see what happens. And you're going to try to work out what A, B, and C could be. I will tell you what kind of chemicals they could be. So they could be an alkane. They could be an alkene. They could be an alkanol, and they could be an alkanoic acid. Okay, so I'm going to do these experiments, and you're going to just watch, and I hope that I will be able to show them properly. And you have to decide what you think they might be. So A, B, and C, and I won't take more than about 10 minutes, and that's it. But here we go. All right, so I'm going to switch cameras, and I'm going to go over to the other camera, and you will be able to see my hands and the experiment and so on. Okay, so here we go. I hope the camera will work. Yes, here it is. Okay, so I'm going over to the other camera. I hope you will be able still to hear me and see what's happening. So the first thing I'm going to do is I'm going to take the three chemicals. Here we are, A, B, and C. And I'm going to add the bromine water to them, okay? So bromine water is really very hazardous, so I'm going to be very careful. But I'm going to take the tops off these, and I'm just going to add a little bit of bromine water to each one of them. Now, what color is bromine water? Bromine water is orange to start with. So I'm going to take a little bit of bromine water here, and I'm going to add some here, here, and here. Now I'm going to put the tops back on, and I'm going to give them a little shake, and we'll see if anything is happening. So here is A. I think you can see that A is not yellow anymore. Okay, so A reacts with bromine water. B, no, it's still yellowish. No reaction. And C, maybe it's reacted a little bit, but I don't really think so. I think it's still yellow. Okay, so A, B, C. I'll just go back to the other camera, and you will see how I'm going to record this. Here we are. So I've got, those are the chemicals it could be, and I've got A, B, C. I've got bromine water, and my question is, does it react or not? And yes, no, not sure, but I don't think so. Okay, the next thing I'm going to do is purple potassium manganate. It will help you if you say the color of different chemicals. So if you go purple potassium manganate, you will find that you remember it easier. So back to the other camera. Here we go. So there's the bromine waters. Now I'm going to get rid of those, and I'm going to get some more A, B, and C. Here's more A, B, and C. Okay. So A, B, and C, now what I'm going to do is I'm going to add some acid to each one of them. I'm going to add acid because potassium manganate has to have acid in it. So I'm going to just add some ordinary sulfuric acid. Just going to add a bit now, put some in first. One of the things you might notice is that of these liquids which I have, A is forming two layers. I don't know if you can see that very easily, but it's forming two layers. It's not mixing. And B is not mixing, but C seems to mix. That could help us. Okay, now I'm going to add the potassium manganate 7. Now, potassium manganate 7 is okay. It's a very purple color, very beautiful purple color. Oh, that's really good. Here we go. Here's some purple, and I'm just putting a few drops into each one of them. And something is happening already. I'll put the tops back on so I can shake them just a little. You may be able to see that A has already changed, okay? A has gone clear. B, nothing. You can probably see the two layers now, but nothing happening. And C, it's reacted. Okay, so here's the results. Let's go back to the other camera. So now we have A has reacted, B no reaction, C has reacted, okay? Now we have one final thing which I'm going to do. I'm going to set fire to them. So let's set fire to them. Here we go. Back to the camera. Okay, so I've got some of each of them and I'm going to set fire to them in order in these, okay? So I'm going to take some of A. I'm just going to take a little bit of A, small amount of A. And I'm going to set fire to it. So here we are. Let's get a little bit closer. Okay. Match. Ah, that is quite a yellow flame. And there's, I don't know if you can see, but there's quite a lot of smoke. That's quite a lot of smoke. And it is making the dish a little bit black on the inside. Around here, it's a little bit black. So it is producing soot, okay? You see that? I'll move that out, ouch, out of the way. Here is some of B. I'll set fire to some B. In a minute, I'm going to be asking you what you think they might be, okay? So here's some B. Set light to some B. Here we go. That is much cleaner. It is still a yellow flame, but it is not leaving soot. It is not a smoky flame. It's quite a clean flame. And I think you can probably see this is quite clean there. This is the one from A, and it has this black stuff. But this one doesn't produce that. And finally, C. Here's C. So chuck some of C in. I tell you what, let's do something different with C. Here's C. And you can see that C disappears quite quickly. It's a very clean flame. Very clean flame. This is almost non-luminous. If I contrast that with A, it's very, very different. Okay? All right. So here comes your puzzle. So here we are. So burning. This is very smoky yellow flame. This is clean yellow flame. This is clean blue flame. This one is cleaner than that one, but they are both clean. Okay. So, Genesis Tumaini, what are these? What are A, B, and C? I remind you, they could be alkane, alkene, alkanol, alkanoic acid. Okay, what do you think? This is a very common type of question where they tell you that this happens and that happens and so on. And what I want to know is what you think they might be. Has anybody got any ideas? So I remind you, A, reacted with bromine water. This purple potassium manganate, this is oxidizing agent, okay? So it can be oxidized and it burns with very smoky flame. B, does not react with bromine water, does not react with this, quite clean to burn. This one maybe reacts with bromine water, not obvious, possibly not, does react with oxidizing agent, burns clean. So what do we think? What do we think? Alkane, alkene, alkanol, alkanoic acid. Anybody want to tell me what they think? Anybody? Fatma, is there anybody there? Michael, is there anybody there who might like to have a guess at what they are and write them down and say? Because you got to try and do this, guys. You got to be able to work it out. Anybody feeling strong? Anybody want to say what A is or what B is or what C is? Come on, let's get brains moving. Come on. I know you can do this. Fatma, have you got somebody there? Michael, Fatma produced the answers last time. Can you find somebody with the answers? Not the same chemical. Not the same chemical. Alkene. A little bit further away. Sorry, alkane. A is an alkene. Okay, Genesis. 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 Okay, we've got A for an alkene. B for an alkane. And C for an alkanol. Genesis. Genesis, that's Tumaini's thought. Genesis, do you agree with A being an alkane? Sorry, an alkene, yes or no? Not convinced. Too many people there going, I'm very tired. I can't answer this. I had 3 hands from Genesis. Is that it? Tumaini, do you all think that A is an alkene? Yes, no, or I don't know. Okay, all right, some people. Okay, good. Thank you very much, guys with the white shirt, pink at the back. Good. Okay, A is an alkene. The clue is it reacts with bromine water and it has a smoky flame. Anything reacts with bromine water and has smoky flame, alkene. Second one, whoever it was who said, they reckon B was an alkane. Do you agree? Genesis. Genesis, is B an alkane? Not an alkane. Have courage. Oh, they agree. Okay. Tumaini, does everybody agree or do some people think, I don't know, I don't know? Oh, well, a lot of people say yes.
Yeah.
Right, it's right. And the clue is this. There is no reaction with bromine water. It cannot be oxidized, but it burns with a clean flame. Okay, that's good. And the last one is the alkanol. And it is the alkanol because although they don't normally react with bromine water, they can be oxidized. And they are oxidized to alkanoic acid. So this here means it is alcohol going to alkanoic acid. And this here shows that it is not high proportion of carbon like alkene. The only smoky ones are alkene and alkyne, okay? Now, last thing, very last thing, I promise, this is it. Next time, we will look at this. And what I will be asking you to do is to tell me whether you know how to turn these, turn these into each other. So I'm going to be asking you how I turn glucose into alkanol, alkanol into alkanoic acid, alkene into alkane, etc., etc. Okay, so that's the idea. Next time I will send this to you and I will send you the answers to all the questions from today's lesson. And I hope it's been useful. But this time next week, we will be doing that, how we turn one chemical into another one, okay? So until next week, I have to go now. It is late for your lunch, but it's my lunch time. So I hope that was useful. If it was useful, great. If not, you're too clever already and you don't need me. If you find something that you want to do, a particular part of the specification of the syllabus, tell me, tell Fatma, tell Michael, they will tell me, and then I can do it particularly next time. But next time, I'm going to be looking at how do we turn one chemical into a different one, okay? And questions to do with that. I will send you some questions for that, but for now, from very windy, raining, cold UK to you where the sun is shining, bye, okay?
Bye-bye, bye-bye.
Bye-bye, guys. Bye-bye. Thank you. Well done. Very smart, Genesis. Very clever, Tumaini. Very good. Well done.
Asante, Teacher Mark.
Well done, Mark. Thank you.
Asante. Kwaheri.
Yeah, good. Hey.
What?
Teacher Collins has appeared suddenly. I can see Teacher
Has he?
Collins. Yes, he's in
Is
the
that
class there.
Is that?
Yes.
Oh, okay.
He
Standing.
was in the class, yeah, behind Fatma.
Ah, do we want to have a quick word?
Fatma, is that Teacher Collins behind you?
Fatma, is Teacher Collins there? No.
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 What's the name of that teacher?
It's just some geezer. It's just somebody who's just walked in off the street and is he's just going through stealing people's money. It's bad.
He's assisting the students. I can see him looking at the books.
I know.
We'll
Thank
get
you,
feedback.
guys. Thank you very much.
Bye-bye.
Okay,
Bye-bye.
see you later.